Have you ever looked up at the night sky and felt that spark of wonder, that sense of awe that comes from realizing just how vast the cosmos truly is? Even on the clearest of nights, what we see with our own eyes is only the smallest glimpse into an ocean of stars, galaxies, and cosmic mysteries waiting to be uncovered. What if I told you that everything we think we know about the universe, everything we've mapped, measured, and observed, is just the tiniest fraction of what's really out there? We're living in an era of unprecedented discovery, where astronomers and physicists are revealing truths about our expanding universe that stretch our imaginations and challenge our understanding of reality itself. In this video, we're setting off on a journey through space and time to explore 25 of the most astounding facts about our ever-growing cosmos. From the mind-bending reality of dark energy pushing galaxies apart at ever-increasing speeds, to the possibility of parallel universes existing just beyond the edge of our perception, each of these facts invites us to rethink our place in this vast, evolving tapestry. This isn't just a list of trivia, it's an invitation to expand your mind alongside the universe, to marvel at phenomena that are at once beautiful, mysterious, and almost unbelievable. Whether you're new to astronomy or a seasoned stargazer, there's something here that will leave you in awe. So settle in, open your mind, and get ready to see the cosmos in a whole new light. We're about to dive deep into the science, the mysteries, and the sheer grandeur of an expanding universe, one astonishing fact at a time. Our journey begins with a revelation that fundamentally rewrote our cosmic story. For much of the 20th century, the prevailing wisdom was that the universe, while expanding from its fiery birth in the Big Bang, must be slowing down. It seemed like simple logic. After all, gravity is the great cosmic glue, an attractive force pulling everything together. Scientists believed that while the expansion might continue forever, it would do so at a gradually decreasing pace, like a ball rolling up a gentle hill, destined to eventually slow to a near stop. But the universe, it turns out, had a spectacular surprise in store. In the late 1990s, two independent teams of astronomers were using the most powerful telescopes on Earth and in space to peer back in time. They were studying a specific kind of stellar explosion known as a Type 1, a supernova. These events are cosmic miracles because they always release the same predictable amount of light. This makes them what astronomers call standard candles, a known brightness that allows us to accurately gauge their distance. By measuring how much the light from these supernovae has been stretched or redshifted as it travels across the expanding universe, we can also determine how fast the galaxy hosting the explosion was moving away from us. The researchers were looking at incredibly distant and therefore ancient supernovae. They expected to see that the expansion was decelerating over time. Instead, the data painted a shocking opposite picture. The most distant supernovae were fainter than they should have been, meaning they were farther away than predicted. The inescapable conclusion was that the universe's expansion isn't slowing down at all. It's speeding up. Galaxies are flying apart from each other at an ever-increasing rate, as if some mysterious, repulsive force is overpowering the pull of gravity itself. This monumental discovery was so profound and paradigm-shifting that it earned the leaders of the two teams the Nobel Prize in Physics in 2011. This acceleration has truly staggering implications for the ultimate fate of everything. If this continues, the distant future of the cosmos looks lonely and cold. Billions of years from now, the acceleration will have pushed all other galaxies so far away that their light can no longer reach us. The night sky for any future civilizations in our own Milky Way will be almost completely black, empty of all other islands of stars. Eventually, even individual galaxies may be torn apart, leading to a scenario cosmologists call heat death. A state where the universe is an impossibly vast, dark, and frigid emptiness, with all energy and structure ultimately fading into a uniform, silent equilibrium. It's a profoundly humbling thought, but it all begins with that one shocking fact. The cosmos isn't just growing, it's rushing outward faster and faster into the unknown. So what is this mysterious force, this anti-gravity that is actively stretching the very fabric of space-time itself? Astronomers gave it a name that perfectly captures our complete lack of understanding: dark energy. And its dominance over the cosmos is the second astounding fact on our list. We now know that this enigmatic energy isn't just a minor player. It makes up roughly 68% of all the mass and energy in the entire universe. To put that into a truly humbling perspective, all the stars, planets, nebulae, black holes, and every single atom that makes up everything we can see and touch, all the so-called normal matter, accounts for less than 5% of the cosmic budget. Dark energy is the silent, invisible majority shareholder of the cosmos, and its primary function appears to be to push. It works in direct opposition to gravity's relentless pull. Where gravity wants to gather, cluster, and condense, dark energy wants to separate, expand, and dilute. Think of it like this. Imagine the universe is a vast loaf of raisin bread baking in an oven. The raisins are galaxies. As the dough rises, every raisin moves away from every other raisin. This is the classic analogy for the expansion of the universe. But with dark energy, it's as if the yeast in the dough suddenly became supercharged, causing the loaf to not just rise, but to expand at a faster and faster rate, ensuring the raisins will one day be so hopelessly far apart that they'll never know the others exist. This repulsive force is so potent that it didn't just win the tug of war against gravity, it completely took over the game billions of years ago. The most mind-bending part of this story involves perhaps the most famous scientist of all time. Albert Einstein, while developing his theory of general relativity, encountered a problem. His equations insisted that a universe filled with matter should either be expanding or contracting, but the scientific consensus at the time, including his own belief, was that the universe was static and eternal. To force his equations to describe a static universe, he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a kind of repulsive energy embedded in the vacuum of space itself that would precisely counterbalance the gravitational collapse of the cosmos. Years later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously discarded his own idea, calling the cosmological constant his biggest blunder. The incredible twist is that modern discoveries about dark energy have resurrected Einstein's rejected concept. It turns out his blunder wasn't a mistake at all. It was a stroke of genius, a prediction of a force he had no way of confirming. The cosmological constant is now the leading candidate for what dark energy actually is: a property of empty space itself that causes it to exert a negative pressure, generating more repulsive force as the universe grows larger and creates more empty space. It's a beautifully simple yet profoundly strange explanation. We can't see dark energy directly, but we can see its monumental effects etched across the cosmos. Supercomputer simulations of the universe's evolution map out an intricate cosmic web of dark matter and galaxies, and when scientists model the influence of dark energy into these simulations, they watch as this invisible force begins to stretch the vast voids between galactic superclusters, accelerating the entire structure's expansion over billions of years. These virtual universes, when they match our real-world observations, provide some of the strongest evidence we have for dark energy's pervasive presence. It is the ghost in the cosmic machine, an emptiness that pushes, whose discovery has left us with more questions than answers, fundamentally challenging our quest to understand the ultimate nature of reality. Yet for all its profound influence, dark matter remains utterly invisible to our eyes and our telescopes. It doesn't emit, absorb, or reflect any form of light or electromagnetic radiation. It's not like a dark cloud of smoke or a shadow. It is an entirely different kind of substance that simply does not interact with light at all. So how do we even know it's there? We detect it the same way we might sense a powerful wind on a dark night, not by seeing the wind itself, but by observing its profound effects on everything around it. The primary way we know dark matter exists is through its immense gravitational pull, a force so strong it literally bends the fabric of reality around it. One of the most compelling pieces of evidence comes from watching how galaxies spin. Think of our own Milky Way, a vast pinwheel of stars, gas, and dust. All of these objects are orbiting the galactic center, held in their paths by the gravitational pull of all the mass inside their orbit. Based on the amount of glowing, visible matter we can see, physicists can calculate how fast stars on the outer edges of the galaxy should be moving. The laws of gravity tell us that these distant stars far from the central bulge should be orbiting relatively slowly. But when astronomers actually measure their speeds, they find something astonishing. Stars on the galactic outskirts are whipping around at nearly the same high speed as those closer in. It's as if the entire galaxy is spinning as a single, solid plate. The only possible explanation for this is that the galaxy is embedded within a massive, invisible sphere of matter, a dark matter halo, that provides the extra gravitational glue needed to hold these fast-moving stars in their orbits. Without this unseen mass, the galaxy would simply fly apart. Perhaps the most dramatic and beautiful demonstration of dark matter's presence is a phenomenon called gravitational lensing. This is a direct consequence of Einstein's theory of general relativity, which tells us that mass bends the space-time around it. The more mass there is in a region of space, the more it warps the paths of light rays traveling through it. A massive cluster of galaxies, which we now know is filled with a huge amount of dark matter, acts like a colossal cosmic lens. When light from an even more distant galaxy passes through this warped region of space-time on its way to our telescopes, its path is bent and distorted. Astronomers see multiple smeared or stretched out images of the background galaxy, forming arcs and rings of light around the foreground cluster. By meticulously mapping these distortions, scientists can essentially create a mass map of the cluster. They can pinpoint exactly where the gravity is strongest, and the result always shows that the vast majority of the mass, the source of this incredible lensing power, is completely invisible. It's not where the galaxies are, it's in the immense dark spaces between them. Given its dominant role in shaping the cosmos, the hunt to directly identify what dark matter actually is constitutes one of the greatest scientific quests of our time. The prevailing theory is that it is likely made up of a new, yet to be discovered type of elementary particle that rarely, if ever, interacts with normal matter. The leading candidate for decades has been a theorized particle known as a WIMP, or weakly interacting massive particle. As the name suggests, these particles would have mass and would interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Deep underground, in abandoned mines and beneath mountains, incredibly sensitive experiments are running in a desperate attempt to catch a fleeting glimpse of one of these particles. These labs are buried to shield them from the constant cosmic rain of other particles that could create false signals. They use vats of ultra-pure liquid xenon or other materials, hoping that on a very rare occasion, a passing dark matter particle will bump into an atomic nucleus and create a tiny, detectable flash of light or charge. So far, these direct detection experiments have yet to find definitive proof, but the search continues to narrow down the possibilities, bringing us closer to perhaps the most monumental discovery in modern physics. But for all our incredible progress in mapping the cosmos, there remains a fundamental and deeply puzzling question that astronomers are still struggling to answer. Exactly how fast is the universe expanding? This brings us to our fourth astounding fact. The universe doesn't seem to be giving us a straight answer, and this controversy, known as the Hubble tension, might be the most exciting clue we have that points toward entirely new physics. The rate of the universe's expansion is called the Hubble Constant, named after Edwin Hubble, whose observations first revealed our cosmos was growing larger. Pinpointing this number is like finding the master key to cosmology. It tells us the age of the universe, helps us calculate distances to faraway objects, and essentially sets the cosmic clock. For decades, astronomers have been working to measure this constant with ever greater precision. The problem is, two of our most reliable and sophisticated methods keep giving us different answers. It's like having two incredibly accurate stopwatches that stubbornly refuse to agree on the time. One method involves building what scientists call the cosmic distance ladder. This technique starts right here in our local cosmic neighborhood. We use geometry to get precise distances to nearby stars, then use those stars to calibrate the brightness of more distant objects like Cepheid variable stars and Type I, a supernova. These become our standard candles. By measuring how fast these galaxies are moving away from us and carefully plotting their distance, we can measure the Hubble constant directly. This local measurement is incredibly precise, but it gives us a faster expansion rate. The other method takes a completely different approach by looking at the very beginning of the universe. It uses the afterglow of the Big Bang itself, the cosmic microwave background radiation. Satellites like Planck have mapped this ancient light in exquisite detail. By studying the tiny fluctuations in this background radiation, cosmologists can run the cosmic film in reverse. They can take the ingredients of the early universe, the amounts of normal matter, dark matter, and dark energy, and use our established laws of physics to simulate how it should evolve over 13.8 billion years to become the universe we see today. This model predicts a Hubble constant value that is slower than the one we get from the local measurements. The discrepancy between these two results is what we call the Hubble tension. And it's not a small, easily dismissed margin of error. These are two of the most well-tested measurements in all of science, each backed by a Nobel Prize, and they disagree by a significant amount. This isn't just a case of scientists needing better calculators. It strongly suggests that there might be something fundamentally incomplete in our model of the universe. Our standard model of cosmology, known as lambda CDM, is incredibly successful at describing so much of what we see, but this tension is a persistent crack in its foundation, a hint that we might be missing a crucial piece of the puzzle. This is where the real excitement lies for physicists. A discrepancy like this doesn't mean one team is wrong. It often means everyone is right, and the universe is trying to tell us something new. Perhaps dark energy isn't a constant force as Einstein proposed, but a dynamic field that has changed in strength over the history of the cosmos. Maybe dark matter has properties we haven't yet discovered, allowing it to interact with itself or with light in strange, subtle ways. Some theorists have even proposed the existence of entirely new types of subatomic particles or forces that were present in the early universe and subtly altered its evolution, creating this mismatch between the ancient and modern expansion rates. Resolving the Hubble tension could very well be the path to our next great breakthrough, a revolution in physics that would expand our understanding of reality itself. It's a thrilling reminder that science at its best is a process of questioning, of finding inconsistencies that push us toward deeper truths. The universe is presenting us with a magnificent mystery, and the entire cosmological community is on a grand detective hunt for the answer. But to truly understand the very beginning, we have to rewind the cosmic clock even further back, to a time so early that our current laws of physics start to break down. This brings us to our next astounding fact, a concept so radical it feels like science fiction, yet it is a cornerstone of modern cosmology, the theory of cosmic inflation. For decades, the Big Bang theory was incredibly successful, but it left cosmologists puzzling over a few nagging problems. Why does the universe, when we look out in every direction, appear so remarkably uniform? The temperature of the cosmic microwave background is the same everywhere to an astonishing degree of precision, just 1 part in 100,000. How could regions of space on opposite sides of the observable universe, which seem to have never been in contact with each other, have reached this identical temperature? It would be like walking into a grand concert hall and finding that every single seat, without any communication, was set to the exact same perfect temperature. This is known as the horizon problem. Another puzzle was the flatness of the universe. Our measurements indicate that the geometry of the cosmos is almost perfectly flat on the largest scales, meaning parallel lines will never meet or diverge. This is an incredibly precarious and specific condition. For the universe to still be so flat after nearly 14 billion years of evolution, its initial geometry must have been fine-tuned to an unimaginable degree of perfection, like balancing a pencil on its tip and having it remain standing for billions of years. This seemed like too much of a coincidence. In the early 1980s, a young physicist named Alan Guth proposed a breathtakingly elegant solution to all these puzzles at once: the theory of inflation. He suggested that in the first fleeting fraction of a second after the Big Bang specifically, from about 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, the universe underwent a period of hyper-exponential expansion. During this fantastically brief instant, the cosmos didn't just grow. It exploded in size, inflating from something trillions of times smaller than a single proton to about the size of a grapefruit. To put that rate of growth into perspective, it would be like expanding a single atom to the size of our entire solar system, and then doing it again in less time than it takes for light to cross that atom. This incredible growth spurt happened faster than the speed of light. Now, that might sound like it violates Einstein's theory of relativity, but it doesn't. Relativity states that no object within spacetime can travel faster than light. Inflation was an expansion of spacetime itself. The fabric of the cosmos was stretching, and there's no speed limit on that stretching. This process of inflation provides the elegant answers we were looking for. It explains the uniformity because before inflation, the entire observable universe was a tiny subatomic patch. Every part of it was in intimate contact, able to easily reach a uniform temperature before being suddenly and spectacularly stretched apart to become the vast cosmos we see today. It also explains the flatness. Imagine taking a small, wrinkled piece of paper, perhaps the surface of a balloon, and then inflating it to the size of the Earth. From your perspective on the surface, that originally wrinkled and curved surface would now appear incredibly smooth and flat. Inflation did exactly that to the geometry of the universe, stretching any initial curvature so thin that it appears perfectly flat to us today. But perhaps the most spectacular evidence for inflation comes from the cosmic microwave background itself. Inflation wasn't a perfectly smooth process. It was driven by a strange, high-energy field called the inflaton field. On the quantum scale, this field was subject to tiny, random fluctuations, a fundamental jitteriness inherent to all quantum systems. As the universe inflated at a phenomenal rate, these microscopic quantum fluctuations were stretched to astronomical sizes, frozen into the fabric of spacetime as faint ripples in the density of matter and energy. These ripples became the seeds for all future structure in the universe. The slightly denser regions governed by gravity eventually pulled in more matter, growing over billions of years to become the galaxies, stars, and planets we see today. This is a profound connection. The largest structures in our universe, galactic superclusters stretching across hundreds of millions of light years, owe their existence to subatomic quantum vibrations that were amplified during that first split second of inflation. When satellites like Planck map the cosmic microwave background with exquisite precision, they are essentially taking a baby picture of the universe, and the pattern of hot and cold spots they see matches the predictions of inflationary theory perfectly. Those tiny temperature variations, mere millionths of a degree, are the direct imprint of those primordial quantum fluctuations, the blueprint for the cosmic web we inhabit. It means that the grand tapestry of the cosmos was woven from the tiniest threads of quantum mechanics, blown up to a cosmic scale by the most powerful expansion event in history. Now, while inflation provides a stunningly successful explanation for the large-scale structure we see, it forces us to confront an even more staggering possibility about the true nature of the cosmos. It suggests that everything we can possibly see, from the most distant galaxy to the cosmic microwave background, is just an infinitesimally small speck within a reality of incomprehensible vastness. This brings us to our sixth astounding fact, the profound and humbling limits of our own observable universe. We often use the word universe to mean everything that exists, but in a very real sense, we are permanent prisoners within our own cosmic bubble. The reason for this is deceptively simple. The universe has a finite age and light has a finite speed. The cosmos is about 13.8 billion years old, which means the most distant light that could have possibly reached us has been traveling for 13.8 billion years. This creates a sphere around us with a radius of 13.8 billion light years, right? Well, not exactly. Here's where it gets truly fascinating. Because the universe has been expanding throughout that entire journey, the source of that ancient light is now much, much farther away. The galaxy that emitted a photon of light 13 billion years ago has continued to drift away from us as that photon was in transit. By the time that light finally completes its epic journey and lands in the sensor of the James Webb Space Telescope, that original galaxy is now about 46.5 billion light years away. Since we can see in all directions, this gives us an observable universe that is roughly 93 billion light years across. It is a colossal volume of space, but it is crucially, definitively finite. Within this sphere, the inventory is almost beyond comprehension. Astronomers estimate there are around 2 trillion galaxies, each a gravitationally bound island of billions or even trillions of stars. This is our cosmic home, the only part of existence we will ever have direct evidence of. And yet, the most current cosmological theories strongly suggest this is not the entire story. The universe beyond our cosmic horizon is likely just more universe, more galaxies, more stars, more planets, stretching on for distances that could be truly infinite. Because the expansion of space between us and those ultra-distant regions is happening so fast, and because that expansion is accelerating, the light from those places can never cross the gulf to reach us. They are forever beyond our view, receding into a permanent darkness. A powerful way to visualize this is to think of yourself standing in the middle of a vast, foggy ocean. The fog represents the opaque plasma of the early universe. As we look out in space and back in time, we eventually hit a wall, the cosmic microwave background, which is the moment the fog cleared and light could travel freely. Now imagine that this ocean is also rapidly growing larger. You can only see a certain distance in every direction, limited by the clarity of the water and the time light has had to travel from a distant object to your eyes. This visible circle around you is your observable universe, but you know the ocean extends far, far beyond what you can see. Some parts of the ocean are moving away from you so quickly, carried by the currents, that waves from those regions can never possibly reach you. They exist, they are real, but they are permanently outside your perceptual bubble. This has a profound philosophical implication. It means there are events happening right now, the births and deaths of stars and civilizations in galaxies so distant that their light will never, ever reach Earth. We are not at the center of this bubble. The cosmic microwave background shows us that every point in the universe has its own unique observable universe, its own cosmic horizon. What we see is not the universe, it is simply the part that is causally connected to us. The rest is an eternal mystery, a reminder that for all our powerful telescopes and brilliant theories, our view of reality is ultimately and fundamentally local. Now, if we want to measure this grand expansion, to put numbers to the speed of this great cosmic getaway, we need a universal speedometer. And nature, in its infinite wisdom, provided us with one, etched into the very light from distant galaxies. This brings us to our seventh astounding fact, the phenomenon of redshift, a subtle stretching of light that serves as our primary evidence for an expanding universe and allows us to measure its rate. To understand redshift, it helps to start with a more familiar concept, the Doppler effect. You experience this every time an ambulance speeds past you. As it approaches, the sound waves from its siren are compressed, pushing them closer together, which raises the pitch. As it moves away, the waves are stretched apart, lowering the pitch. Light behaves in a remarkably similar way. When a source of light is moving toward us, the light waves are compressed, shifting them toward the blue end of the spectrum. When it's moving away, the waves are stretched, shifting them toward the red end. For nearby objects within our own galaxy, this Doppler shift is indeed caused by their actual motion through space. But when we look at distant galaxies, we encounter something far more profound. The redshift we see isn't primarily from galaxies hurtling away through space like cosmic bullets. Instead, it is caused by the expansion of space itself in the vast gulf between us and them. Imagine you have a stretchy rubber sheet and you draw a wave pattern on it, a series of peaks and troughs. Now, if you slowly pull the sheet taut, stretching it, what happens to that wave? The entire pattern gets longer. The peaks move farther apart, the wavelength increases. This is precisely what happens to light as it travels across the expanding universe. The fabric of spacetime itself is stretching during the light's multi-billion-year journey, and this stretches the light waves along with it. The longer the light has been traveling, the more stretching it has endured and the greater its redshift. It's a direct measure of how much the universe has expanded since the moment that photon began its voyage. The man who first uncovered this cosmic secret was the astronomer Edwin Hubble. In the 1920s, using the most powerful telescope of its time at Mount Wilson Observatory, Hubble was meticulously studying mysterious spiral nebulae, working to determine their true nature and distance. He made two groundbreaking discoveries. First, by identifying a special kind of star called a Cepheids variable in the Andromeda Nebula, he proved conclusively that these spirals were not mere clouds within our own Milky Way, but were themselves island universes, galaxies millions of light years away, vastly expanding the known size of the cosmos. His second, even more revolutionary discovery came when he combined his distance measurements for these galaxies with spectroscopic data collected by his colleague Milton Humason. This data showed the light from these galaxies was systematically shifted toward the red end of the spectrum. Not only were most galaxies moving away from us, but Hubble found a clear and stunning pattern. The farther away a galaxy was, the greater its redshift, and therefore the faster it appeared to be receding. This relationship, now enshrined as Hubble's law, was the smoking gun. The entire universe was not static, as everyone had believed for so long. It was dynamically expanding, with galaxies all rushing apart from one another. The most direct way to see this evidence is to look at a galaxy's spectrum. Every galaxy's starlight, when passed through a spectroscope, produces a unique barcode, a series of dark lines at specific wavelengths corresponding to the chemical elements present, like hydrogen and oxygen. For a nearby galaxy that isn't moving very fast, these lines will appear right where we expect them in the lab. But for a distant galaxy, this entire barcode is shifted. Every single line is moved in unison toward the red. The degree of that shift is a direct fingerprint of the expansion the light has witnessed. By carefully measuring how far those familiar lines have slid toward the red, astronomers can calculate not just the galaxy's velocity, but because of Hubble's law, its distance as well. Redshift, denoted by the letter Z, has become the fundamental ruler for mapping the cosmos. This discovery fundamentally redefined our place in the universe. We are not at the center of some grand retreat. There is no center. From the perspective of any galaxy, every other galaxy would appear to be moving away, with more distant ones receding faster. It's the raisins in the expanding loaf of raisin bread all over again. The redshift is the indelible mark of the universe's growth, a constant reminder that we live in a dynamic, evolving cosmos that has been stretching the very fabric of reality for billions of years. But how can we be so confident about the geometry of something as vast as the entire cosmos? The evidence for a flat universe comes from a source we've already marveled at, the cosmic microwave background. Think of those tiny temperature fluctuations, the hot and cold spots in the ancient light, as a kind of cosmic fingerprint. The apparent size of these spots as they appear on the sky is incredibly sensitive to the overall geometry of the universe. It works on a principle similar to how the curvature of a lens distorts an image. In a closed, spherical universe, space-time would act like a magnifying glass, making the spots appear larger than they truly are. In an open, saddle-shaped universe, it would have the opposite, minimizing effect. But when satellites like Planck measured these spots with phenomenal precision, they found their apparent size was just right. There was no magnification or minimization at all. The light traveled in straight lines across the cosmos, meaning the geometry of the universe on the largest scales is flat. The angles of a giant cosmic triangle really do add up to 180 degrees. This finding of flatness is more than just a geometric curiosity. It has breathtaking implications for the ultimate fate of everything. The geometry of the universe is directly tied to its destiny through the balance between its expansion energy and the gravitational pull of all the matter and energy within it. A closed universe with enough matter and energy to curve space-time back on itself would eventually stop expanding and collapse in a dramatic Big Crunch. An open universe with too little density would expand forever, but its expansion would gradually slow down, leading to a cold, thin, and lonely end. Our flat universe represents the precise, critical balance between these two extremes. However, with the shocking discovery of dark energy, this balance takes on a new and dramatic meaning. That perfect density for flatness is now overwhelmingly dominated by this repulsive force, which means the expansion isn't just continuing, it's accelerating. The most likely fate for our flat universe is not a gradual slowing, but an eternal and ever faster expansion, ultimately leading to that cold, dark, and isolated state known as the heat death. This precise balance required for flatness presented cosmologists with a major puzzle, one so significant it's called the flatness problem. For the universe to be as flat as we measure it to be today, some 13.8 billion years after the Big Bang, its initial conditions had to be fine-tuned to an almost unbelievable degree of perfection. In the very first second, the density of the universe must have been balanced to within 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. To visualize such an incomprehensible number, if you were to write it out, it would be longer than the distance across our solar system in millimeters. This level of perfection seems like an impossible coincidence. This is where the theory of cosmic inflation provides its elegant solution. That period of hyper-fast expansion didn't just make the universe uniform, it also made it flat. Imagine the surface of a partially inflated balloon. It might have all sorts of wrinkles and curves, but if you inflate that balloon to an enormous size, the tiny patch of surface you can see from your perspective appears completely flat. Inflation did exactly that to the entire cosmos. It took any initial curvature and stretched it so thin that it became smooth and flat to within our ability to measure, perfectly explaining why we find ourselves in a universe with such a precise geometric balance. But to truly map the expansion history of the universe, we need more than just standard candles. We need a standard ruler, and etched into the very large-scale structure of the cosmos is a fossilized measuring tape of incredible precision, a relic from a time when the universe was too hot and dense to be transparent. This is the phenomenon of baryon acoustic oscillations, and it provides some of the most robust and independent evidence we have for the existence of dark energy and the accelerating expansion. To understand this, we have to travel back to the universe's first 400,000 years, to that same hot, dense plasma of particles and light that would eventually release the cosmic microwave background. In this primordial soup, gravity was trying to pull matter together into clumps, but it faced a powerful opposing force: pressure. Imagine a region where dark matter and normal matter, which astronomers call baryons, are slightly denser than their surroundings. Gravity wants to collapse this over-dense region, pulling more material in. But the incredible heat and pressure from the photons of light packed into that space create a counterforce pushing outward. This tug-of-war between gravity's inward pull and radiation's outward pressure set up powerful sound waves or acoustic oscillations that rippled through the plasma at over half the speed of sound. These weren't gentle ripples, they were massive pressure waves traveling through the entire visible universe, and they traveled for nearly 400,000 years until the universe cooled enough for a pivotal moment: recombination. When electrons and protons combined to form the first neutral hydrogen atoms, the photons were suddenly set free, creating the CMB. But just as importantly, the pressure waves lost their driving force. The sound waves instantly froze in place, leaving behind spherical shells of matter regions that were slightly more dense because the wave had pushed material outward as it traveled. The maximum distance one of these sound waves could travel before the universe became neutral became a fixed standard scale. Think of it like dropping a pebble into a pond and then instantly freezing the entire pond solid. The ripples are preserved, locked in ice at a specific distance from the center. This frozen distance, this standard ruler, is about 500 million light-years across. After recombination, these spherical shells of slightly enhanced matter density served as preferred locations for galaxies to form over billions of years. This means that if we could map the positions of millions of galaxies in the universe today, we should see a subtle preference for galaxies to be separated by this specific distance. It's a faint echo of those ancient sound waves, a ghostly pattern imprinted on the cosmic web, and that is exactly what astronomers have found. Massive galaxy redshift surveys, like the Sloan Digital Sky Survey, have painstakingly mapped the three-dimensional positions of millions of galaxies. When they statistically analyze this vast cosmic cartography, a stunning pattern emerges. There is a clear, statistically significant excess of galaxy pairs separated by approximately 500 million light-years. It's as if we're seeing the faint, fossilized imprint of those primordial ripples. By measuring the apparent size of this standard ruler at different cosmic epochs, by looking at galaxy maps from both the nearby and the very distant universe, astronomers can measure how much the universe has expanded over time. This technique provides a powerful and completely independent confirmation of the accelerating universe. When they measure the baryon acoustic oscillation ruler at a distance corresponding to billions of years ago, it appears one size. When they measure it in the more recent universe, it appears larger because the expansion of the universe has stretched the ruler itself. The rate of this stretching tells us the history of the expansion, and it clearly points to an acceleration, a finding that aligns perfectly with the supernova and CMB data. It's a triumphant convergence of evidence, with the faint whisper of sound waves from the dawn of time telling us the same incredible story as the death throes of ancient stars. This foundational idea that the universe on its grandest scales is fundamentally fair and unbiased is known as the cosmological principle. It's a powerful assumption that makes the entire science of cosmology possible, and it states two key things. First, the universe is homogeneous. This doesn't mean every single cubic light-year is identical. Obviously, a void is different from a galactic supercluster. It means that if you take a sufficiently large bird's eye view, say, By smoothing out the cosmos into cubes a few 100 million light-years on a side, the average density of matter and energy is the same everywhere. The second part is that the universe is isotropic. This means it looks the same in every direction you look. No matter where you point your telescope, the large-scale properties of the cosmos are identical. There is no preferred direction, no cosmic north or south. This principle is the ultimate argument against the idea that we occupy a special or privileged place in the universe. For centuries, humanity clung to the notion that Earth was the center of creation. The cosmological principle is the scientific rebuttal to that ancient vanity. It asserts that the laws of physics are the same everywhere and that any observer in any galaxy at any time would see roughly the same large-scale universe that we do. Their observable universe would be centered on them, just as ours is centered on us, and they would see galaxies receding in all directions, supporting the same cosmological models. Our strongest evidence for this principle comes from two incredible sources. The first is the cosmic microwave background. That baby picture of the universe shows a stunningly smooth and uniform plasma, with temperature variations of just 1 part in 100,000. No matter which direction we look, this ancient light tells the same story of a hot, dense beginning. The second piece of evidence is the large-scale distribution of galaxies. When we create three-dimensional maps from massive surveys, we don't see a single giant structure or a sudden edge. Instead, we see a vast cosmic web of filaments and voids that extends for billions of light-years, and this web appears statistically the same in every volume of space we can observe. It is a universe of grand patterns, not of unique, solitary features. However, science always questions its own assumptions, and some astronomers are investigating whether this principle might need a slight tweak. They point to potential anomalies like the mysterious cold spot in the cosmic microwave background, a region that is unusually cold and large, or the intriguing and controversial suggestion of a Hubble tension on a grand scale, where the expansion rate might seem slightly different in one part of the sky versus another. Could these be mere statistical flukes in our data, or might they be hints that on the very largest scales, beyond what we can easily see, the universe has some form of grand structure or imbalance that we haven't yet fully comprehended? For now, the cosmological principle remains the bedrock of our understanding, a testament to a universe that is vast, uniform, and wonderfully predictable in its grand design, ensuring that the cosmos is a place we can actually hope to understand. Considering the relentless acceleration driven by dark energy, the ultimate destiny of our universe appears to be a profoundly cold and lonely one. This leading scenario, often called the Big Freeze or heat death, is a direct consequence of the expansion not just continuing but speeding up indefinitely. Imagine the distant future, trillions of years from now. The galaxies we see today as our neighbors will have long since vanished from our view, their light stretched far beyond the red into undetectable wavelengths as they are carried away by the stretching fabric of space itself. Our local group of galaxies, bound together by gravity, might coalesce into a single, giant elliptical galaxy, but it will become an isolated island in a sea of ever-growing blackness. Beyond its borders, there will be nothing to see. The cosmic microwave background will have faded to a whisper, its energy so redshifted and diluted that it is effectively gone. The universe will be a vast, dark, and empty expanse, having expanded so much that the average temperature plummets to a fraction of a degree above absolute zero. This isn't just about things getting farther apart. It's about the universe slowly running out of the energy needed to create and sustain complexity. In this far future, the era of star formation will have long since ended. All the interstellar gas and dust, the raw material for new suns, will have been either consumed by previous generations of stars or become so thinly spread across the colossal voids that it can no longer collapse to form new ones. One by one, the stars themselves will burn out, the massive, brilliant blue stars will be the first to go, exploding in supernova after just a few million years. Medium-sized stars like our Sun will spend their fuel and shed their outer layers, leaving behind white dwarfs that will cool for eons into cold black diamonds. The smallest, dimmest red dwarf stars will stubbornly fuse their hydrogen for trillions of years, but eventually even their faint fires will flicker and die. The universe will be left with the stellar corpses, a dark graveyard of black holes, neutron stars, and cold white dwarfs drifting endlessly apart. But the story doesn't necessarily end even there. Over timescales so vast they dwarf the current age of the universe, even these dark remnants face their own eventual dissolution. This is where we venture into the realm of theoretical physics and concepts like proton decay. If protons, the building blocks of all atomic nuclei, are not truly stable but have an unimaginably long half-life, then even the dead Earth and every white dwarf would, over perhaps 10 to the power of 40 years, simply evaporate into a diffuse sea of subatomic particles and radiation. Black holes, the most durable structures in the universe, are not completely eternal either. Through a quantum mechanical process at their boundaries called Hawking radiation, they slowly lose mass and energy. A stellar mass black hole might take 10 to the power of 67 years to evaporate, while a supermassive one could take 10 to the power of 100 years. In the very, very end, the universe could be an inconceivably vast, utterly dark, and nearly perfect vacuum, populated only by the faintest of particles and radiation, evenly spread out with no energy differences left to drive any process whatsoever, a state of maximum entropy and final equilibrium. There is, however, a more dramatic and violent alternative fate known as the Big Rip. This scenario depends on the precise nature of dark energy. If its repulsive force, its so-called equation of state, becomes stronger over time instead of remaining constant, it could eventually overcome all other forces in the universe. Not just the gravitational pull between galaxies, but the forces that hold galaxies, solar systems, and even atoms themselves together. In this apocalyptic vision, the accelerating expansion would first tear apart galaxy clusters, then individual galaxies. As the end draws near, the relentless pull of expanding space would rip stars from their planetary systems and planets from their stars. In the final moments, the fabric of space-time would stretch so violently that it would overcome the electromagnetic force holding our bodies together, and even the strong nuclear force binding atomic nuclei. The universe would end not with a whimper, but with a catastrophic shredding of every last bit of structure, down to the most fundamental particles. While current observations of the cosmic microwave background and supernova currently favor the more gradual Big Freeze scenario, the true nature of dark energy remains one of physics' greatest mysteries, leaving a sliver of possibility for a far more abrupt and dramatic conclusion to the cosmic story. This concept of a fixed horizon brings us to one of the most profound and humbling realities of our existence: the limits of our own observable universe and the vast unknowable realms that lie beyond it. The spherical region of space from which light has had time to reach us since the Big Bang is known as our Hubble volume. It is our ultimate cosmic prison, the only part of existence we will ever have direct observational access to. We've already touched on its immense size, about 93 billion light-years across, but its true nature is even more fascinating. The edge of this sphere isn't a physical boundary, it's a horizon in time. It's the point where the finite age of the universe and the finite speed of light create a fundamental limit to what we can see. Now, here's where it gets truly mind-bending. Because the universe is expanding, and that expansion is accelerating, the composition of our Hubble volume is constantly changing. Distant galaxies that are currently within our observable universe are not fixed residents. They are like swimmers caught in a powerful current. As the fabric of space continues to stretch, galaxies that are already receding from us at tremendous speeds will eventually be carried away by the accelerating expansion. There will come a point for each of these distant islands when their recession velocity, driven by the expansion of space itself, exceeds the speed of light. This doesn't break any laws of physics, as nothing is moving through space faster than light. It's the space between us that is growing at a rate that prevents any future communication. When this happens, a galaxy will effectively cross our Hubble horizon. The last photons it emits will be forever in transit, never able to bridge the ever-widening gulf. From our perspective, that galaxy won't just get fainter. It will gradually fade to black, its light redshifted into complete undetectability before it winks out of our observable universe entirely. Its story will be over for us. Future astronomers, if any are still around billions of years from now, will look up at a much emptier sky. The evidence for the Big Bang, the cosmic microwave background, will have redshifted into oblivion. The distant galaxies we see today will have vanished, leaving behind only the gravitationally bound local group of galaxies to which our Milky Way belongs. The universe for them will appear static and island-like, with no clues to suggest it was ever once a vast, expanding cosmos teeming with light. This leads to a staggering philosophical implication. We confidently use the word universe to mean all of existence, but we must confront the very real possibility that everything we can see, every piece of data we have, represents only a tiny fraction of the whole. The universe beyond our cosmic horizon is likely just more universe, more galaxies, more stars, more planets, stretching on for distances that could be infinite. And because of the nature of the expansion, we are forever cut off from it. We are like a person stranded on a small island in a fog-shrouded ocean. We can see a certain distance in every direction, but we have no way of knowing what lies beyond the fog. We can use our instruments to deduce the properties of the ocean based on our limited view, but we can never know if there are other islands, other continents, or even entirely different oceans out there. This means there are events happening right now, the births of stars, the collapses of civilizations, perhaps even the evolution of life, in galaxies so distant that their light will never, ever reach Earth. They are real, they are part of the same physical reality, but they are fundamentally and forever unknowable to us. It forces a profound humility upon science. For all our powerful telescopes and brilliant theories, our view of reality is ultimately and fundamentally local. We are not at the center of this bubble. The cosmic microwave background shows us that every point in the universe has its own unique observable universe, its own cosmic horizon. What we see is not the universe, it is simply the part that is causally connected to us. The rest is an eternal mystery, a silent reminder that the greatest discoveries may always lie just beyond our grasp. But with that firm number in hand, a truly baffling paradox seems to emerge, one that often confuses even the most ardent space enthusiasts. If the universe is only 13.8 billion years old, and nothing can travel faster than light, then logic would suggest that the most distant object we could possibly see should be 13.8 billion light-years away. So how is it that we can observe galaxies whose light has traveled well over 13 billion years to reach us, yet those same galaxies are now calculated to be over 30 billion light-years from Earth? This apparent contradiction is one of the most common sources of confusion in cosmology, and the resolution lies in a critical distinction that changes everything: the difference between the distance light has traveled and the distance to the object now, due to the relentless expansion of the universe. Imagine a photon of light setting out on its journey from a very young galaxy, just 1 billion years after the Big Bang. That photon is headed in our direction, moving at light speed through the fabric of space-time. However, while this photon is in transit, the very fabric it's moving through is itself stretching. It's like a tiny ant trying to cross a vast rubber sheet that is being steadily pulled taut in all directions. The ant is making progress, but the finish line is moving away even faster. For most of cosmic history, the expansion rate was slower, allowing the light to make headway. But as the photon gets closer to us, the expansion between us and its point of origin has been accumulating over billions of years. By the time that photon finally arrives at our telescope, the galaxy that emitted it has been carried away by the expansion of space to a distance that is much, much greater than the mere 13.8 billion light-years the photon physically traveled. The light tells us the look-back time, how long ago it left, while redshift measurements and our cosmological models tell us the object's current, much larger distance. There's no faster than light travel violation here. It's the space between the objects that has grown, carrying the galaxies apart. This precise and verified age of the universe is far more than just a fascinating piece of trivia. It is the essential bedrock upon which we build and test our entire understanding of cosmology. The number 13.8 billion years acts as a master key, a critical parameter that helps to lock in all the other values in our standard model of cosmology, known as lambda CDM. This model describes a universe with specific amounts of normal matter, dark matter, and dark energy. The age of the universe is deeply intertwined with the Hubble constant, the rate of expansion. A faster expansion rate would imply a younger universe, as it would have taken less time for galaxies to reach their current separations. A slower expansion rate would suggest an older universe. When we measure the Hubble constant using local distance indicators like supernova and Cepheid variables, we get a value that, when plugged into our models, should give us the age of the universe. That calculated age must then be consistent with completely independent measures of age, like the maturity of the oldest stars in globular clusters and the exquisite details of the cosmic microwave background. The fact that these wildly different methods, one looking at the local, modern universe and the other looking back to its very infancy, converge on the same number, 13.8 billion years, is a spectacular triumph for modern science. It gives us tremendous confidence that our model, while undoubtedly incomplete, is fundamentally on the right track. Any proposed tweak to the model, whether it's a new property of dark energy or a novel type of neutrino, must first and foremost not break this beautiful, consistent timeline. The age of the cosmos is the ultimate arbiter of cosmological truth, a silent clock that started ticking at the moment of the Big Bang and to which all our theories must synchronize. Now, let's turn our attention to the oldest photograph ever taken, a picture of the universe in its infancy. This is the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. It is the most ancient light we can observe, a relic from a time when the cosmos was a mere 380,000 years old. To put that age into perspective, if the universe's entire history were compressed into a single calendar year, this light was emitted around 9 p.m. On January 1st, it is the foundational background hum of creation, and it fills every cubic centimeter of the space around us. Right now, as you watch this, trillions of these primordial photons are passing through your body every second, a silent whisper from the dawn of time. This incredible radiation is the direct result of one of the most pivotal events in cosmic history, an event cosmologists call recombination. For the first several 100,000 years of its existence, the universe was far too hot and dense to be transparent. It was a searing, opaque plasma, a roiling soup of protons, electrons, and photons. Light particles couldn't travel any meaningful distance without immediately crashing into a free electron, like a person trying to walk through a dense, frenzied crowd. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped to around 3,000 Kelvin, cool enough for electrons to finally be captured by protons to form the first stable hydrogen atoms. This process is called recombination, though it was actually the first time these particles had ever combined. In an instant, the cosmic fog cleared. The free electrons were suddenly imprisoned in atoms, and the photons, which had been constantly scattered, were finally set free. They could now travel across the universe in straight lines, largely unimpeded. The light that was released at that moment has been traveling ever since, stretched and cooled by the expansion of the universe over the ensuing 13.8 billion years. What was once a brilliant, visible light flash has been redshifted by a factor of about 1,100. Its wavelength stretched by the expanding fabric of space all the way into the microwave part of the spectrum. Today, we detect it as a uniform glow bathing the entire sky, with a temperature of just 2.725 degrees above absolute zero, incredibly cold, but not quite the utter chill of empty space. The discovery of this background radiation in 1964 was one of the greatest accidental breakthroughs in science. Two astronomers at Bell Labs, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna for radio astronomy experiments. They kept detecting a persistent, mysterious microwave static that came from every direction in the sky. It was unaffected by the time of day or the season, and it wouldn't go away no matter what they did. They even famously cleaned out a buildup of pigeon droppings from the antenna, but the irritating noise remained. They had inadvertently stumbled upon the echo of the Big Bang itself. Unbeknownst to them, a team at Princeton University, led by Robert Dick, had been actively searching for this very signal, having predicted its existence as a necessary consequence of the hot Big Bang model. When the two groups connected, the penny dropped. Penzias and Wilson had found the smoking gun evidence for the Big Bang, a discovery for which they would later win the Nobel Prize. That faint, uniform hiss was the cooled remnant of the universe's fiery birth. But the true power of the cosmic microwave background isn't just in its existence, it's in its intricate details. While the CMB is remarkably uniform, it is not perfectly smooth. When satellites like NASA's COBE mission first mapped the entire sky in the 1990s, they discovered tiny, minuscule fluctuations in temperature, tiny variations of about 1 part in 100,000. These are the seeds of all future structure. Those slightly warmer spots are regions of space that were ever so slightly denser, where the gravitational pull was a tiny bit stronger. Over billions of years, that extra gravity acted as an anchor, pulling in more and more dark matter and gas, eventually growing into the vast cosmic web of galaxies and galaxy clusters we see today. The cooler spots were the slightly emptier regions that would evolve into the great cosmic voids. The entire architecture of our universe was imprinted on this ancient light. The most detailed map ever made of this cosmic blueprint comes from the European Space Agency's Planck satellite. Its all-sky map looks like an oval, technicolor portrait of the universe at 380,000 years old, mottled with blobs of red, blue, and yellow. Each color represents a tiny deviation from the average temperature. This map is so exquisitely precise that it allows cosmologists to read the universe's vital signs like a doctor reading a medical chart. By analyzing the statistical patterns of these hot and cold spots, their sizes, and how they are correlated with each other, scientists can determine the exact composition of the universe with incredible accuracy. It is from the Planck data that we get our most precise numbers. The universe is made of about 4.9% normal matter, 26.8% dark matter, and 68.3% dark energy. Furthermore, the patterns in this light allow us to test our most fundamental theories of physics and confirm the story of cosmic inflation. The specific signature of the temperature fluctuations, the way they are distributed across different angular scales on the sky, matches the predictions of inflationary theory perfectly. It strongly supports the idea that those initial quantum fluctuations were indeed stretched to cosmic size during that period of hyper-fast expansion. The cosmic microwave background is therefore far more than a static relic. It is an active data stream, a fossilized message from the earliest moments of time that continues to tell us in incredible detail the story of where we came from and what the cosmos is made of. It is our most powerful time machine, giving us a direct snapshot of the infant universe and confirming our deepest theories about its origin and evolution. But those tiny temperature variations in the cosmic microwave background, those seeds of future structure, needed a powerful force to nurture them into the grand cosmic architecture we see today. That force is gravity, and the story of how it sculpted the universe brings us to our next astounding fact: the formation of the vast, web-like structure that defines the cosmos on the largest scales. This incredible transformation from a nearly uniform plasma to a universe filled with brilliant galaxies separated by immense voids is an epic tale of growth that took billions of years to unfold. It all began with those tiny density fluctuations imprinted by inflation. Think of the early universe after recombination as a canvas with an almost imperceptible texture. Some areas were ever so slightly denser, like a patch of slightly thicker paint, while others were a bit thinner. In the denser regions, there was just a little more mass, which meant a slightly stronger gravitational pull. This gravity acted like a cosmic magnet, very slowly starting to pull in the surrounding dark matter and gas. While this process started immediately, it was initially a painfully slow one, as the overall expansion of the universe was working against it, trying to pull everything apart. For hundreds of millions of years, the universe was a dark, quiet place, with these slight overdensities gradually gathering more and more material, growing in the background like a slow-motion avalanche. The true heroes of this story, the unseen architects of the cosmic web, are the gravitational effects of dark matter. Because dark matter doesn't interact with light or with itself through any force other than gravity, it was free to begin collapsing into structures long before normal matter could. Normal matter, the protons, electrons, and atoms that make up stars and planets, was held back by pressure. If you try to squeeze a gas, it pushes back. But dark matter felt no such pressure. It could simply flow inward under the influence of gravity, forming vast, invisible halos and deep gravitational wells long before the first star ever ignited. These dark matter structures provided the essential scaffolding, the gravitational skeleton upon which the visible universe would later be built. Without this unseen framework, the force of gravity alone would not have been strong enough to overcome the expansion of the universe and the pressure of normal matter to form the galaxies we see today. Once these dark matter halos reached a critical mass and density, their gravitational pull became powerful enough to overcome the pressure of the normal matter gas. Vast rivers of hydrogen and helium gas, the pristine fuel for the first stars, began to flow along the filaments of dark matter, funneling into the deepest gravitational wells. It was at the intersections of these dark matter filaments within the largest halos that the first protogalaxies began to form. This was the dawn of a new era as the first stars, known as population 3 stars, ignited in a brilliant flash, ending the cosmic dark ages and flooding the universe with its first true light. These first stars were likely behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying young in spectacular supernova that seeded the cosmos with the first heavy elements. Over billions of years, this process continued in a grand cycle of construction. Smaller structures merged to form larger ones through a relentless gravitational dance. Dwarf galaxies collided and merged to form larger galaxies like our Milky Way. Those galaxies themselves were then drawn together by the immense gravity of the dark matter scaffolding, forming groups, clusters, and eventually the largest structures in the universe, superclusters. These are not gravitationally bound structures themselves, but rather vast filaments and walls of galaxies that trace out the underlying cosmic web. Our own Milky Way resides on the outskirts of the Laniakea supercluster, a colossal structure containing over 100,000 galaxies, all moving collectively towards a gravitational focal point known as the Great Attractor. We can actually witness this grand design through massive sky surveys like the Sloan Digital Sky Survey. By meticulously mapping the three-dimensional positions of millions of galaxies, astronomers have revealed that the universe is not a random scatter of points. Instead, galaxies are arranged in a breathtakingly intricate network of dense filaments, massive clusters at the nodes where filaments intersect, and enormous, seemingly empty voids in between. This cosmic web is the largest pattern in nature, a universe-spanning architecture that evolved from the most minuscule of beginnings. The power of our understanding is showcased in supercomputer simulations that model this entire process. Cosmologists can input the initial conditions from the cosmic microwave background, add the known ingredients of dark matter and dark energy, and then let the laws of physics play out virtually. The results of these simulations are nothing short of miraculous. They show the formation of a cosmic web that is statistically identical to the one we observe in the real universe. We can watch as dark matter first collapses into a delicate web-like structure, and then see the normal gas follow, lighting up the filaments with virtual galaxies. The fact that these simulations, running on the laws of physics we have deduced here on Earth, can recreate the large-scale structure of the entire observable universe is one of the strongest validations of our entire cosmological model. It confirms that the story of our cosmos, from quantum jitters to galactic superclusters, is not just a compelling narrative, but a physical reality written in the laws of gravity and the fundamental properties of matter and energy. This brings us to one of the most fundamental and often misunderstood concepts in all of cosmology, the true nature of the universe's expansion itself. It's a subtle distinction, but getting it right is absolutely essential to visualizing the cosmos accurately. The galaxies are not simply flying apart from each other through a static, pre-existing space like shrapnel from an explosion. That is a classic and very common misconception. Instead, what is happening is far more bizarre. The very fabric of space-time itself is stretching, and it is this stretching that carries the galaxies away from one another. This is what cosmologists call the metric expansion of space. Think of the universe not as an empty stage, but as the surface of a balloon. Draw several dots on a deflated balloon. These are your galaxies. Now start inflating the balloon. As the rubber surface stretches, what happens? Every single dot moves away from every other dot. There is no center to the expansion on the surface. From the perspective of any dot, all the others are receding. The dots themselves aren't moving across the surface. They are being carried apart by the stretching of the material they are embedded within. This is a powerful analogy for our expanding universe. The galaxies are like those dots, and space itself is the stretching rubber. This distinction resolves one of the biggest head-scratchers in relativity. How can galaxies be moving away from us faster than the speed of light? It seems like a direct violation of Einstein's cosmic speed limit, but the rule that nothing can travel through space faster than light remains completely intact. The key is that the galaxies aren't traveling that fast. The space between us and them is growing. There's no limit to how fast the fabric of space-time itself can stretch. For galaxies sufficiently far away, the cumulative expansion across the vast gulf separating us adds up to a recession velocity that indeed exceeds light speed. This doesn't break physics, it is a direct prediction of it, and it defines the very edge of our observable universe. This expansion is a property of the vacuum itself, and in theory, it affects everything from the vast voids between superclusters down to the space between atoms. However, on small, local scales, you don't see your ruler growing or the solar system getting larger. Why? Because other forces are vastly more powerful. On the scale of solar systems, galaxies, and even galaxy clusters, the gravitational bonds between objects are incredibly strong. This gravity has long since overcome the expansion, holding these structures together as stable, bound systems. The expansion's effect is only noticeable across the truly enormous, empty voids between these gravitationally bound structures. It's the cosmic equivalent of drawing two dots very close together on our balloon. As you inflate it, those two dots will move apart a tiny, imperceptible amount because the rubber between them stretches only a little. But a dot on the opposite side of the balloon will zoom away because all the stretching rubber in between adds up to a huge distance. The expansion only wins where gravity has already lost in the great cosmic deserts between the oases of galaxies. While the balloon analogy is wonderfully intuitive, it does have its limitations, chiefly the fact that a balloon expands into the air around it, giving it a center and an edge. Our universe does not. A more abstract but more accurate way to visualize it is with an infinite coordinate grid, like a vast piece of graph paper where every line is being stretched simultaneously. Imagine every galaxy is fixed to a point on this grid. Now, as time moves forward, the grid itself expands. The lines move further apart. The galaxies don't change their grid coordinates, but the physical distance between those coordinate points increases. The space itself is dilating. This is what we mean by the metric expansion of space. It's not that things are moving to new locations on a static map. The scale of the map itself is changing. This is why the expansion has no center. Every point on the grid is moving away from every other point uniformly. Wherever you are in the universe, you would see the same thing. Distant galaxies receding, with the most distant ones moving away the fastest. It is a fundamental property of the cosmos, a silent, relentless stretching that has been underway since the very first moments of time, shaping the destiny of everything on the grandest of scales. This profound uniformity presents one of the most significant puzzles in cosmology, known as the horizon problem. To truly appreciate why this is so baffling, we need to consider the concept of causality and the ultimate speed limit of the universe, the speed of light. In the standard Big Bang model without inflation, there simply hasn't been enough time since the beginning of the universe for light or heat to have traveled between these vastly separated regions to equalize their temperatures. Imagine two students sitting at opposite ends of a gigantic cold lecture hall. If they each have a small space heater, they can warm up their immediate area, but the heat from one student's heater cannot possibly reach the other student in time to warm them up. They exist in separate, isolated environments, or what physicists call causally disconnected regions. Now scale that up to the cosmic level. The cosmic microwave background shows us that the entire sky, in every direction, was at the same temperature when the universe was only 380,000 years old. But if we calculate how far light could have traveled in that time, the maximum distance any signal or influence could have possibly spread, we find a shocking result. That distance, known as the cosmic horizon, is far smaller than the separation between those two opposite sides of the observable universe at that time. In the standard Big Bang model, these regions on opposite sides of the sky could never have exchanged information or heat. They were like islands in a vast ocean that had never been connected. There was no possible physical mechanism for them to have coordinated their temperature to such an exquisite degree of precision. It would be like our two students in the lecture hall discovering, to their astonishment, that they were both exactly 72.3 degrees warm without ever having communicated or shared heat. This presented a monumental challenge to the standard model, a paradox that suggested a crucial piece of the cosmic story was missing. The theory of cosmic inflation provides the breathtakingly elegant solution to this conundrum. It proposes that these regions that now appear impossibly far apart were, in fact, once intimately connected in the universe's first fleeting fraction of a second. Before the period of inflation, the entire observable universe was compressed into a volume much smaller than a single atom. At that unimaginable scale, every single point was in direct causal contact with every other point. They were neighbors, able to easily exchange energy and reach a perfectly uniform temperature. Then inflation occurred, that moment of hyper-exponential expansion. This process did not just gently nudge these regions apart. It stretched the very fabric of spacetime itself at a rate far exceeding the speed of light, catapulting these once close points to opposite ends of the cosmos. The key insight is that this expansion was a stretching of space itself, not motion through space, so it did not violate the laws of causality. The thermal equilibrium, that perfect uniform temperature, was established before inflation when the entire universe was a tiny, subatomic connected whole. Inflation then simply took that established uniformity and stretched it across a volume billions of light years across, preserving it like a pattern on a balloon that is inflated to an enormous size. What we see in the cosmic microwave background is not a coincidence that requires explanation. It is the natural consequence of a universe that was once small enough to mix thoroughly before being blown up to a cosmic scale. Inflation solves the horizon problem by providing a mechanism for the entire observable universe to have been in causal contact, allowing it to smooth itself out before the incredible expansion that created the vast distances we see today. And so we arrive at one of the most profound and beautiful ideas in all of science, a concept that connects the unimaginably small to the impossibly large. It's the story of how the grand tapestry of the cosmos, every galaxy, every star, every planet owes its existence to the tiniest, most fleeting whispers of reality at the quantum scale. This is the incredible journey from quantum jitters to cosmic structure. To understand this, we have to venture into the bizarre world of quantum mechanics, a realm where emptiness is not truly empty. Even in a perfect vacuum at the tiniest scales, there is a fundamental fizzing energy. Particles and antiparticles spontaneously pop into existence for inconceivably brief moments before annihilating each other and vanishing again. This isn't just theoretical. We can measure the effects of these quantum fluctuations in laboratories here on Earth. They represent a basic, inherent uncertainty woven into the fabric of reality itself. Normally, these fluctuations are utterly insignificant, affecting only the subatomic world. But in the very first instance of our universe, something extraordinary happened that would amplify these microscopic tremors into the blueprint for all creation. That something was cosmic inflation. Remember that period of hyper-exponential expansion when the universe grew from 1 billion times smaller than a proton to the size of a grapefruit in a fraction of a second. During this incredible growth spurt, the universe wasn't just expanding. It was also filled with a strange, high-energy field known as the inflaton field. And like all quantum fields, it was subject to these tiny, random fluctuations. Here's the crucial part. As the universe inflated at a staggering rate, it didn't just stretch the fabric of space. It also stretched these microscopic quantum fluctuations in the inflaton field. A tiny random jump in energy here, a minuscule dip there, these were all frozen into the expanding fabric of spacetime itself, imprinted as faint ripples in the density of matter and energy. Think of it like recording a whisper. If you whisper into a microphone and play it back at a normal volume, it's still a whisper. But if you record that same whisper and then play it back through a massive stadium sound system at maximum power, you've amplified it into a deafening roar that fills the entire arena. Inflation was that cosmic sound system. It took quantum whispers, vibrations on a scale 1 trillion times smaller than an atom, and stretched them to astronomical sizes, freezing them in as regions that were ever so slightly more or less dense than their surroundings. These ripples became the cosmic seeds, the initial conditions for all structure that was to follow. After inflation ended and the universe settled into the more gradual expansion of the hot Big Bang, gravity went to work on these seeds. The slightly denser regions had a tiny bit more gravitational pull. Over hundreds of millions of years, this extra gravity acted as an anchor, slowly pulling in more and more dark matter and gas from the surrounding areas. The under-dense regions, conversely, lost material to their denser neighbors, eventually evolving into the vast cosmic voids we see today. This gravitational amplification is what turned those initial quantum imprints into the first stars, the first galaxies, and ultimately, the vast cosmic web of filaments and clusters that defines the large-scale universe. This revelation is nothing short of breathtaking. It means that the majestic Pinwheel Galaxy, the immense Virgo supercluster, and even our own Milky Way can trace their ultimate origin back to a random quantum fluctuation that occurred in a volume of space trillions of times smaller than a single proton. The largest structures we can observe were literally birthed from the smallest possible physical phenomena. This is arguably one of the most significant connections ever made in science, a direct bridge between the two great pillars of 20th century physics: quantum mechanics, which governs the world of the incredibly small, and general relativity, which describes the universe on the largest scales. For a long time, these two theories seemed completely separate, describing different realms with different rules. But the story of inflationary fluctuations shows they are deeply intertwined, working together to create the universe we inhabit. The evidence for this is written across the sky in the cosmic microwave background. The pattern of hot and cold spots we see in that ancient light is not random noise. Its statistical properties, the sizes of the spots and how they correlate with each other, match the predictions of quantum fluctuations amplified by inflation with stunning precision. When we look at that map from the Planck satellite, we are essentially looking at a quantum mechanical photograph, a snapshot of those primordial density variations taken when the universe was only 380,000 years old. It is the most powerful validation that our universe, in all its splendor and complexity, was indeed born from a quantum seed. Now, if we were to take a complete inventory of everything in the cosmos to write down a full recipe for the universe, the results would be both humbling and astonishing. After centuries of scientific discovery, after building telescopes that can peer back to the dawn of time, we have arrived at a profound and somewhat unsettling conclusion. Almost everything that makes up the universe is completely invisible to us. The grand cosmic recipe is fundamentally mysterious. If you could gather all the mass and energy in the universe into one pie, that pie would be sliced into 3 vastly unequal pieces. The smallest slice, a mere 5%, is everything we've ever known, everything we've ever touched, and every form of light we've ever seen. This is so-called ordinary or baryonic matter. It encompasses every single atom in every star, every planet, every nebula, and every living thing. It is the material that built galaxies and sparked life. And yet, it is a tiny, almost insignificant fraction of the whole. The remaining 95% of the universe is made of substances we cannot see, substances that do not interact with light in any way, and whose fundamental nature remains one of the greatest mysteries in all of physics. The larger of these two invisible slices, making up about 27% of the cosmic pie, is dark matter. We've already explored its gravitational effects, how it holds galaxies together and forms the scaffolding for the cosmic web. But what exactly is it? We know it has mass and exerts a gravitational pull, but it does not emit, absorb, or reflect light. It simply does not interact with electromagnetic radiation. It is not black holes, nor is it made of any known particle. The leading candidate for decades has been a theorized particle known as a WIMP, a weakly interacting massive particle, which would interact only through gravity and the weak nuclear force. Yet, despite decades of searching with incredibly sensitive detectors buried deep underground, we have not directly caught one. Other candidates, like actions or even sterile neutrinos, are also in the running. The hunt for dark matter is a global scientific endeavor, a painstaking process of elimination that continues to push the boundaries of our technology and our understanding of particle physics. But the most dominant ingredient, the true majority shareholder of the cosmos, is also the most enigmatic. Dark energy makes up a staggering 68% of the universe. This is not a substance in the traditional sense, but rather a property of space itself, a repulsive force that causes the expansion of the universe to accelerate. Its discovery overturned our most fundamental assumptions about cosmic destiny. Unlike dark matter, which pulls things together through gravity, dark energy pushes everything apart. The leading explanation is that it is Einstein's cosmological constant, a fixed energy density inherent to the vacuum of empty space. As the universe expands and creates more space, more of this repulsive energy comes into existence, fueling the acceleration. Alternative theories suggest dark energy could be a dynamic field nicknamed quintessence that changes over time, but for now, its true nature is almost entirely unknown. We see its monumental effect on the fate of the entire cosmos, but we have no idea what it actually is. This breakdown is perhaps the most humbling realization in all of science. For all our achievements, our species has managed to study and understand only 5% of the contents of the universe. The other 95% is a complete mystery, a blank canvas upon which we are still trying to paint a picture. It is a stark reminder that our perception of reality is limited. We are like beings who can only perceive the surface of an ocean, unaware of the vast, dark, and powerful currents flowing beneath. Our entire visible universe, with its hundreds of billions of galaxies, is just the visible froth on top of a deep, dark sea whose composition we are only beginning to guess at. This isn't a closed chapter, it is the wide-open frontier of cosmology, inviting a new generation of telescopes, experiments, and brilliant minds to finally illuminate the darkness. But this breathtakingly precise balance of dark energy, this delicate value of the cosmological constant that allows for galaxies and life to form, presents us with perhaps the most shocking and embarrassing problem in all of theoretical physics. It's a problem of numbers so wildly out of alignment that it suggests either a profound gap in our understanding or a cosmic coincidence of unimaginable proportions. This is the cosmological constant problem, and it reveals a stunning disconnect between the two great pillars of modern physics, quantum mechanics and general relativity. To understand the problem, we need to consider what quantum theory tells us about the very nature of empty space. We often think of a vacuum as being truly empty, a void of nothingness. But according to quantum field theory, this is completely wrong. Empty space is not empty at all. It is a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles spontaneously pop into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and vanishing back into nothingness. This isn't just a mathematical quirk. We can observe the effects of this quantum froth in experiments like the Casimir effect, where two metal plates placed very close together in a vacuum are gently pushed together by the pressure of these virtual particles fluctuating outside them. All of this frantic activity means that the vacuum of space itself must possess a certain energy density. Every cubic centimeter of nothingness is actually brimming with this zero-point energy. When physicists attempt to calculate how much energy this quantum vacuum should have, they do so by adding up all the possible ways these virtual particles can fluctuate. The result they get is not a small number, it is colossal. The theoretical prediction for the vacuum energy density is approximately 10 to the power of 113 joules per cubic meter. This is often cited as the worst prediction in the entire history of science. Now, let's look at the other side of the equation. We observe the effects of dark energy through the accelerating expansion of the universe. We can measure its strength from the cosmic microwave background and distant supernova. The observed value of the cosmological constant, which represents the energy density of dark energy, is about 10 to the power of -9 joules per cubic meter. Let that discrepancy sink in. The theoretical prediction from quantum mechanics is about 120 orders of magnitude larger than the value we actually observe. That's a 1 followed by 120 zeros. To try and visualize a number that vast is almost impossible. If the predicted value were correct, the repulsive force of this vacuum energy would have been so unimaginably strong that it would have ripped apart every atom, every nucleus in the first fraction of a second after the Big Bang. Galaxies, stars, and life would never have had even the slightest chance to form. The universe would be an utterly empty, featureless void. This isn't a small rounding error, it's a chasm of misunderstanding. It's as if we predicted the weight of the entire observable universe, but then went out and measured the weight of a single proton and found they were supposed to be the same. The two theories are giving us answers that are fundamentally, catastrophically incompatible. It suggests that our current models are deeply incomplete. We are clearly missing a crucial piece of the puzzle, some mechanism that almost perfectly cancels out this enormous vacuum energy, leaving behind only the tiny, residual amount we measure as dark energy. Physicists have proposed several potential solutions, but none are yet satisfactory. One elegant idea is supersymmetry, a theory that proposes every known particle has a hidden superpartner particle. In a perfectly supersymmetric universe, the contributions of these partner particles to the vacuum energy would exactly cancel out the contributions of the normal particles, resulting in a net zero cosmological constant. The problem is, we haven't found any evidence for these superpartners, and if they exist, supersymmetry must be a broken symmetry in our universe, meaning the cancellation would be imperfect, and we're back to needing an explanation for why the leftover is so tiny. Another, more philosophical approach is the anthropic principle. This line of reasoning suggests that maybe the value of the cosmological constant isn't determined by a fundamental law, but is instead a random variable that can take on different values in different regions of a much larger multiverse. In the overwhelming majority of these universes, the constant is far too large, and those universes are barren and empty. But we find ourselves in a universe where the value is exceptionally small, not because it's likely, but because it's the only type of universe that can possibly have observers in it to wonder about it. It's a selection effect. While this idea is controversial and feels like a retreat from explanation for some, it is taken seriously by many cosmologists as a possible answer to why our universe seems so finely tuned for life. The cosmological constant problem remains a wide-open frontier, a glaring reminder that for all our knowledge, we are still gazing into a profound abyss of ignorance. Resolving this tension between the quantum world and the cosmic realm is perhaps the single greatest challenge for the next generation of physicists and the key to a deeper, more unified theory of everything. But as we confront this staggering discrepancy in the vacuum energy, it forces us to ask a more radical question. Could it be that our entire framework for understanding the cosmos is built on an incomplete picture of reality itself? What if the three dimensions of space we experience are not all there is? This brings us to one of the most mind-expanding ideas in modern theoretical physics, a concept that suggests our entire universe might be a mere slice of a much richer, higher-dimensional existence. This is the world of brain cosmology. In this speculative yet compelling framework, our four-dimensional universe, three of space, one of time, is not the entirety of reality. Instead, it is envisioned as a three-dimensional membrane, or brain for short, floating within a higher dimensional space called the bulk. These extra spatial dimensions could be compactified or curled up into sizes too small for us to perceive, much like how a garden hose appears as a one-dimensional line from a distance but is actually a two-dimensional surface when viewed up close. In the most popular version of this idea, inspired by string theory, the bulk has 10 or 11 dimensions, and our familiar universe is a three-brain within it. This radical shift in perspective offers stunning new ways to address some of cosmology's deepest puzzles. One of the most famous is the hierarchy problem, the perplexing weakness of gravity compared to the other fundamental forces. Gravity is a staggering 10 to the power of 40 times weaker than the electromagnetic force. Why? In brain cosmology, a compelling answer emerges. It's possible that while particles of light and matter, the photons, electrons, and quarks that make up our world, are stuck to our brain like ink on a page, gravity is not. Gravity, described as the curvature of space-time, could permeate all dimensions. If it is free to spread out into the extra dimensions of the bulk, its strength would be diluted from our three-dimensional perspective. The force we perceive as incredibly weak might actually be just as strong as the other forces. It just has more room to spread out, making it seem faint within the confines of our brain. This isn't just a clever analogy. It provides a natural, geometric explanation for one of physics' most baffling imbalances without the need for any artificial fine-tuning. This model also opens the door to breathtaking new explanations for cosmic inflation and even dark energy. Could the initial hyper-fast expansion of our universe have been triggered by a collision with another brain floating in the bulk? Perhaps the mysterious repulsive force of dark energy is not an intrinsic property of empty space on our brain, but a subtle gravitational pull from a parallel brain located a tiny distance away in an extra dimension. In this view, the accelerating expansion of our cosmos might not be driven by something within our universe, but by the influence of another universe entirely, separated from us by a gap in a dimension we cannot see. While these ideas sound like pure science fiction, they are grounded in sophisticated mathematics, and remarkably, they could leave observable fingerprints. If extra dimensions exist, they would subtly alter the way gravitational waves ripples in the fabric of space-time travel across the universe. As these waves propagate, a tiny fraction of their energy could leak into the bulk. This would cause the waves we detect to be ever so slightly weaker than predicted by standard four-dimensional general relativity. The next generation of gravitational wave observatories will be sensitive enough to look for precisely this kind of diminishment. Furthermore, high-energy particle collisions in accelerators like the Large Hadron Collider could, in theory, produce particles or even microscopic black holes that briefly travel into these extra dimensions before decaying, leaving an anomalous signature of missing energy in our detectors. We are, in essence, building machines that can poke and prod at the very fabric of our dimensional reality, searching for tears or leaks that might reveal we are not alone in the bulk. It's a testament to human curiosity that we can conceive of such vast, hidden architectures and then devise experiments to go looking for them. This idea of a vast, higher-dimensional bulk inevitably leads us to one of the most profound and controversial frontiers of cosmology, the possibility that our entire universe is not unique. What if the Big Bang was not a singular creation event, but merely a local happening within a much grander, perhaps infinite, meta-reality? This is the staggering concept of the multiverse, and it emerges almost naturally from the very theory that so elegantly explains our own cosmos, eternal inflation. We've already explored how a brief period of hyper-fast inflation can solve the major puzzles of the Big Bang. But what if inflation, once started, doesn't completely stop everywhere at once? This is the core of eternal inflation. Imagine a universe filled with the inflaton field, the energy field that drives this exponential expansion. This field isn't perfectly uniform. It's subject to those same quantum fluctuations that seeded our galaxies. In most regions, this field will lose energy, settle down, and for that region, inflation will end. The energy of the inflaton field is converted into a hot soup of particles, and a Big Bang begins for that pocket of space. This is how our observable universe was born. But due to quantum jitters in other regions, the inflaton field can tunnel or fluctuate to an even higher energy state. In these patches, inflation doesn't end, it continues, and it continues at a rate that is truly mind-boggling. The space in these regions expands so rapidly that it quickly dwarfs the pockets where inflation has stopped. These eternally inflating regions act as a breeding ground, endlessly spawning new pocket universes where inflation has locally ended. Our entire cosmos, with its hundreds of billions of galaxies, could be just one bubble in a vast, growing foam of universes, each with its own distinct Big Bang event. This leads to a breathtaking consequence. If the inflattened field can take on different values when it decays in different bubbles, then the fundamental properties of each pocket universe could be determined by that random settling. The laws of physics, as we know them, are dictated by the values of about 24 fundamental constants: the strength of gravity, the mass of an electron, the strength of the nuclear forces. In this eternal inflation scenario, each of these constants could be randomly selected in each new bubble universe. Most of these universes might be stillborn or barren. If the strength of gravity were slightly stronger, stars might burn out in millions of years instead of billions, leaving no time for life to evolve. If the nuclear forces were weaker, hydrogen might never fuse into helium, and no stars would shine at all. We find ourselves in a universe with constants that seem curiously fine-tuned for complexity and life, not because it's special, but because it's the only type of universe we could find ourselves in. This is the anthropic principle applied on a cosmic scale, a potential explanation for the puzzling fine-tuning we observe without needing a designer. The philosophical implications of this are enormous. It challenges the very goal of fundamental physics, to find a unique, elegant theory of everything that predicts all the constants of nature. If the multiverse is real, then there is no single prediction. The constants are just environmental, like the temperature and pressure on Earth. They aren't fundamental laws, they are local bylaws, and we simply won the cosmic lottery by being in a bubble where the numbers allow for our existence. For some scientists, this is a cop-out, a retreat from explanation that makes cosmology untestable. For others, it's a profound shift in perspective, moving from asking, why are these constants what they are? To, what is the landscape of possible constants, and what are the conditions for habitable universes within that landscape? This raises the critical question, is the multiverse science or is it just metaphysics? Can we ever test such a grand idea? Proponents argue that yes, there are potential ways to look for evidence. If our universe collided with another bubble universe in the distant past, the immense energy of that collision could have left an imprint on the cosmic microwave background, a kind of cosmic bruise on the sky. Astronomers have actively searched for such anomalous circular patterns in the CMB, though no definitive evidence has been found. Another possibility involves gravitational waves from the inflationary epoch. The specific spectrum of these primordial ripples could tell us about the energy scales involved and potentially provide indirect support for the underlying mechanisms that make eternal inflation possible. While we may never be able to visit another universe, we might find its fingerprints in our own. The multiverse remains one of the most speculative ideas in cosmology, but it is also one of the most compelling, a natural extension of our best theories that forces us to confront the ultimate nature of reality and our place within it. And just when we think we have the cosmos figured out, when our models seem to fit so beautifully with the data, the universe has a way of throwing us a curveball, a mystery so puzzling that it's been given a name straight out of a cosmic thriller, the Axis of Evil. This isn't about some interstellar supervillain. It's the title scientists have given to a series of strange, unexpected alignments found in the most pristine data we have, the cosmic microwave background. These anomalies challenge one of our most sacred cosmological principles, and they hint that either we're making a monumental error or the universe has a preferred direction we never knew about. To understand why this is so shocking, we have to return to the cosmological principle, the foundational idea that the universe is homogeneous and isotropic. On the largest scales, it should have no center, no edges, and no special directions. It should look the same everywhere and in every direction. The CMB is our best test of this principle. After meticulous processing to remove the glare of our own galaxy and other foreground effects, the leftover map of the primordial universe should be a random, Gaussian field of hot and cold spots, a beautiful, stochastic tapestry with no preferred axis or alignment. But when scientists began to study the full sky map from the Wilkinson microwave anisotropy probe and later the Planck satellite, they noticed something peculiar. Certain large-scale features in the temperature fluctuations weren't completely random. They seemed to be subtly aligned with each other and even more bizarrely with the plane of our own solar system. This alignment manifests in a few specific ways. One of the most discussed is the apparent alignment of the quadrupole and octopole moments, which are just fancy terms for the way the temperature variations are distributed across the largest angular scales on the sky. Instead of being oriented randomly, these large-scale patterns seem to have their hot and cold spots lining up along a particular axis that, unnervingly, points close to the ecliptic plane, the disk in which the planets orbit our sun. Furthermore, there's a mysterious cold spot that seems too large and too cold to easily explain, and there are suggestions of a hemispheric asymmetry, where the fluctuations on one side of the sky appear statistically different from those on the other. It's as if the universe's largest scale structures are somehow aware of our tiny, insignificant solar system's orientation, a correlation that should be astronomically impossible under the standard model. The moniker "axis of evil" was coined partly in jest, reflecting how philosophically unsettling this finding is to the core principles of cosmology. If these alignments are real and not an illusion, they strike at the heart of the Copernican principle, the idea that we do not occupy a special or privileged place in the universe. A true preferred axis would mean that on the largest scales, the universe does have a directionality, a fundamental orientation that could point toward entirely new physics. Perhaps dark energy or dark matter has a directional property, a kind of cosmic texture that gives the universe a grain. Or perhaps it's a relic from the pre-inflationary universe, a scar from its earliest moments that inflation didn't completely erase. Some have even speculated, though it's highly controversial, that it could be a sign of our universe brushing up against another in a vast multiverse. Of course, the most likely explanation is far more mundane, but no less important to investigate systematic error. We are, after all, looking out at the universe from deep inside our own galaxy, which is itself filled with gas and dust that emit microwaves. Removing this foreground contamination to reveal the pristine CMB beneath is an extraordinarily complex task. Could it be that our cleaning process is imperfect, leaving behind a faint residue that just happens to align with our solar system's plane? Or perhaps there is an unknown source of emission within our own solar system that we haven't fully accounted for. The fact that the anomaly seems tied to our ecliptic plane is a huge red flag that the problem might be local, a case of us seeing our own reflection in the cosmic window rather than a true feature of the distant universe. The scientific community is deeply divided on the significance of the axis of evil. Many cosmologists argue it is almost certainly a statistical fluke. When you have a dataset as rich and complex as the CMB, you're bound to find some strange-looking patterns purely by chance. We humans are pattern recognition engines. We're hardwired to find significance in randomness. It's the cosmic equivalent of seeing a face in the clouds. Others, however, point out that the probability of such alignments occurring by chance is quite low, and the fact that this particular anomaly has persisted through increasingly precise data releases from both WMAP and Planck demands a thorough investigation, not just a dismissal. Resolving this mystery is a major goal for future observatories. Scientists are developing new, more sophisticated methods to model and subtract foregrounds with even greater precision. The next generation of CMB experiments, which will measure not just the temperature fluctuations but also the polarization of this ancient light with incredible fidelity, could hold the key. If the alignment is a real cosmological feature, it should be imprinted in the polarization patterns as well. If it vanishes in the cleaner data, we'll know it was a ghost in our machine all along. Either way, the investigation into the axis of evil is a powerful example of how science operates at its best. It's not about clinging to dogma, but about following the data, however strange it may lead us. These perplexing alignments, whether a flaw in our measurements or a crack in our models, serve as a thrilling reminder that the universe still has profound secrets left to reveal. But as we continue to push our observations to the very edge of the observable universe, to the most ancient light from the most distant quasars, we are conducting an experiment that probes the very bedrock of reality itself. This brings us to a fact so profound it challenges the core of physics, the possibility that the fundamental constants of nature might not be so constant after all. Imagine the fine structure constant, a number that dictates the strength of electromagnetic interactions between light and matter. It governs how atoms hold together, how stars burn, and is as fundamental to physics as pi is to geometry. For centuries, we've assumed these constants were fixed, immutable pillars upon which the universe was built. But what if the immense expansion of the cosmos, the stretching of space-time itself over billions of years, has subtly tweaked these very pillars? Astronomers test this mind-bending idea by using quasars as cosmic time machines. These incredibly bright beacons, powered by supermassive black holes in the hearts of young galaxies, act as backlights for the early universe. As their light travels for billions of years to reach us, it passes through giant clouds of primordial gas. Atoms within these clouds, like iron, magnesium, and nickel, absorb very specific wavelengths of this quasar light, creating a unique barcode of dark lines in the spectrum. This barcode is a direct fingerprint of the atomic physics at work when the universe was young. The crucial point is that the precise spacing and position of these absorption lines are exquisitely sensitive to the value of the fine structure constant. If this constant had even a slightly different value billions of years ago, the entire barcode would be shifted in a very specific, detectable way. The results from these meticulous experiments are, to put it mildly, controversial. Some teams, after analyzing the light from hundreds of quasars, have reported evidence that the fine structure constant was indeed slightly smaller in the distant past. The shift they report is minuscule, a few parts in a million, but if true, the implications would be earth-shattering. It would mean that the laws of physics are not fixed and universal, they evolve alongside the cosmos. The very rules of the game would have been different when the universe was younger and denser. This would force a complete rewrite of our standard models, suggesting that Einstein's general relativity is incomplete and that we need a new, deeper theory that seamlessly unifies gravity with the other forces in a way that allows for such variation. The scientific community remains deeply divided on this finding. Other teams, using different methods or analyzing different sets of quasars, have found no evidence of any change at all. The potential for hidden systematic errors is enormous. Perhaps the observed shifts are caused by unknown chemical compositions in the gas clouds, or by subtle differences in the temperature and pressure of those ancient environments. The hunt for conclusive evidence continues, driving the development of ever more powerful telescopes and precise spectrographs. Whether these constants are truly constant or slowly changing is one of the most profound questions we can ask, because the answer defines whether the laws of nature are timeless and absolute, or if they are themselves a dynamic part of the cosmic story, evolving alongside the galaxies and stars they help to create. And so we arrive at the final, and perhaps most humbling, fact on our journey, the inevitable end of cosmology itself. We are living in a golden age of discovery, a brief and privileged window in the cosmic calendar where the universe is both old enough to have cooled and structured into galaxies, and young enough that the brilliant, ancient light from its fiery birth is still visible to us. But this window will not be open forever. The same accelerated expansion that we've marveled at throughout this video is slowly but surely closing the blinds on our cosmic view. condemning any future civilizations to a profound and inescapable ignorance about the true nature of the universe. The first clues to vanish will be the distant galaxies themselves. As dark energy continues to push the fabric of space-time apart at an ever-increasing rate, the galaxies we see today will begin to cross our cosmic horizon. Their light, already stretched into the red, will be redshifted into complete oblivion. The wavelengths will become so long, the photons so few and far between, that they will be undetectable against the backdrop of empty space. One by one, island universes will fade from the skies, not with a bang, but with a silent, fading whisper into the infrared and beyond. The universe will appear to be a much smaller, lonelier place, containing only the gravitationally bound local group of galaxies, with the rest of creation having receded into a permanent and impenetrable darkness. Next to disappear will be the most crucial piece of evidence we have, the cosmic microwave background. This faint afterglow, the cooled remnant of the Big Bang, is our direct window to the universe's infancy. But as the expansion continues, this light will suffer the same fate as the galaxies. Its wavelengths will be stretched from microwaves to radio waves, and then to wavelengths longer than the observable universe itself. Its energy will be diluted to such an extent that it will become completely indistinguishable from the quantum noise of empty space. The temperature of the vacuum will asymptotically approach absolute zero, and the last fossil evidence of a hot, dense beginning will be irrevocably erased. For any astronomers in that far future, the sky will not just be dark, it will be silent and utterly featureless, offering no hints of a dynamic, expanding cosmos. This leads to a staggering philosophical dilemma. How would a future scientist born billions of years from now ever deduce the Big Bang, the expanding universe, or dark energy? All the evidence we take for granted would be gone. Their entire observable universe would consist of a single merged galaxy, the result of the Milky Way and Andromeda colliding, drifting in an infinite static blackness. With no receding galaxies to show a redshift and no background radiation to suggest a hot beginning, the prevailing theory would almost certainly be that of a static, eternal, and island universe. They would have no reason to believe in a beginning or in an expansion they could not measure. Cosmology, the science of the origin and evolution of the whole universe, would become impossible. The great cosmic story would be lost simply because the final chapters had stretched so far that the beginning was no longer legible. This forces a profound reflection on our own place in cosmic history. We are not just lucky to be living on a planet that can support life. We are incredibly fortunate to be living at a time when the universe is still transparent, still telling its story. Our era is a special one, a sweet spot between the primordial fires and the eventual eternal cold, where the clues to our origin are still within reach. It bestows upon us a unique responsibility to learn as much as we can, to map the cosmos while the map is still readable, and to preserve this knowledge as a priceless gift for any future generations that might arise in that far more isolated and lonely cosmos. We are the brief guardians of the cosmic narrative, living in the one epoch where the universe can look back at itself and begin to understand its own magnificent history. And so our journey brings us to this moment of reflection, standing beneath a canopy of stars that is both breathtakingly beautiful and profoundly mysterious. The 25 facts we've explored are more than just a collection of trivia. They are a radical reimagining of our place in the cosmos. We've seen how the universe is not static or eternal, but a dynamic, evolving entity, stretching and growing at an ever-increasing rate, propelled by a mysterious force we call dark energy, a force that makes up the majority of everything and yet remains completely invisible to us. We've discovered that the stars and galaxies we can see are just the visible tip of a cosmic iceberg, floating in a vast sea of dark matter, an unknown substance whose gravitational pull sculpts the universe yet eludes every attempt to directly detect it. We've grappled with the Hubble tension, a cosmic controversy that suggests our most precise measurements of the universe's expansion don't agree, potentially pointing the way to new physics we haven't yet dreamed of. We've traced the origin of all structure back to the tiniest quantum fluctuations, amplified to cosmic scales by a period of hyper-fast inflation in the very first fraction of a second, connecting the world of the impossibly small to the grand architecture of galactic superclusters. We've confronted the humbling reality that our entire observable universe, with its hundreds of billions of galaxies, is likely just a tiny bubble in an infinite and eternal multiverse where the very laws of physics might be different. And we've seen how our window to understand all of this is temporary, that the accelerating expansion will one day close the blinds on our cosmic view, leaving future civilizations in a static island universe with no clues to its magnificent beginning. Each of these revelations peels back a layer of reality to show us a cosmos far stranger, more vast, and more wonderful than we could have possibly imagined just a century ago. It is a universe where empty space pushes, where the majority of mass is invisible, and where the largest structures were seeded by the smallest possible vibrations. It is a reality that constantly challenges our intuition and demands we think bigger, pushing the boundaries of our understanding to their absolute limits. This isn't a completed story, it is an ongoing detective saga with new clues waiting in the light of distant supernova, in the subtle patterns of the cosmic microwave background, and in the data from particle colliders deep underground. The greatest takeaway from all of this is not a set of answers, but an invitation to remain curious, to look up at the night sky not as a static painting, but as a dynamic, evolving story that we are only just beginning to read. Every mystery solved reveals two new ones, and that is the thrilling engine of scientific discovery. So we want to hear from you. Which of these 25 facts stretched your mind the most? Was it the shocking dominance of dark energy, the ghostly presence of dark matter, or the brain-bending possibility of a multiverse? Let us know in the comments below. Share your wonder and your questions. If this journey through the expanding universe captivated you, make sure to subscribe and hit the bell so you don't miss our next exploration into the mysteries of space, time, and reality itself. The cosmos is waiting, and its greatest secrets are still out there, waiting to be uncovered by the next generation of curious